is a second set of notes for electrostatics force where we're going to look at Coulombs Law, which is calculating this electrostatic force. Just a reminder, Newton's third law is related to a lot of different things, including this. Here, when you have an electrostatic force, it's caused by charges. And if you have two negative charges, you're going to have an equal and opposite repulsion force. So this would have been an electrostatic force on this guy right here. And this would have been an equal and opposite electrostatic force on that one, since these two negatives would repel each other. Other repulsions would include two positives, and then if you had two opposite signs like a plus and a minus, you can go ahead and you can draw arrows inwards to represent, and these would be the same size because they would be equal and opposite to each other. Once again, one's going right, one's going left, but they're going towards each other, representing an attraction. Here's a question: how much force is on a charge B if there's 26 newtons of force on charge A? Well, it's equal and opposite, so it's going to be 26 newtons over here. And if A was positive, so that's what this question is saying, if that A was positive, what would B have to be for this to be a repulsion? Notice how this arrow is facing away from A, so that's the repulsion, and this would have to be a positive as well. So there's your answer there. And Coulomb's law relates charges to Q1 and Q2, the two different charges, to distance, and it has this K, which is a constant. And for the sake of our lesson, we're always going to use air, so this is actually K air. It's but we're just going to say K because we're only going to do problems in this unit where we're dealing with air. So it's 9.0 times 10 to the ninth, and what you need to know is it's a very strong fundamental force, this electrostatic force. Second strongest fundamental force in nature. We're going to look at strong nuclear force when we get to nuclear physics later on. And you can tell because this K value is such a big number. 9.0 times 10 to the ninth, that's this 9 billion number, and therefore you need smaller charges. Smaller of these charges are required to have a decent sized force. And so this is what I just said talking about air. We're going to deal with air every single time, so just don't worry about the air. That's going to be your K value every single time. Here's some variables we have. Force we saw before, Newton, N. So when we talk about the variables are what you see in the equation. These units are what you see after the number, like 50 newtons. So this is what you would put after when we deal with charge. So K is the electrostatic force constant. It's newtons meters squared divided by Coulomb squared. Don't worry about memorizing this for my class. If you're learning from me for another teacher, you might have to. But this is just there so that when everything's all said and done you're going to have an answer that will be in newtons when you solve for this Coulomb's law problem. Now, when it comes down to charge, if there's more than one charge, you're going to have Q1s and Q2s. But if there's only one charge, or the charge happens to be the same, you might just have a Q in the problems in the equations. Like this one has Q1 and Q2, and the unit is going to be coulombs. So capital C for coulombs. And then finally, you might be given a distance or a radius to fill in here. It's going to be a distance between two objects, and that's going to be the unit meters. So the variable that you might see in some equations, sometimes you might even see a capital Q. So I just want to alert you to that. Many equations, many different books, places where you see them will use a capital Q. But the unit's going to be a coulomb, and a coulomb's a really big number because it's 6.25 times 10 to the 18th. Think about that number. 6.25, 1, 2, 3, 4, 5, 6. I would keep on going. I'd have to take this decimal place 18 times, 18 more zeros past that to actually get to this number. That's a huge number, and each electron brings in a decent amount of charge. And the one we saw before, and since we have such a large charge in a single coulomb, and this is a unit we always have to use coulombs when we're dealing with this equation. These Q's have to be in coulombs. We're often going to see microcoulombs. So anytime you see this microcoulomb symbol that looks like this right here, a little mu, it's like a M and a U. What you're going to do is you're going to take that number and you're going to put times 10 to the -6 next to it. So if you see 5 microcoulombs, in your calculation, you're going to have 5 times 10 to the -6 coulombs. Now watch out, because if you're just given 5 coulombs, you're not going to do that. So it's only when you see 5 micro, that symbol right here, coulombs, that you would add this times 10 to the -6 to the value. So we have our Charles Augustin de Coulomb, this guy right here. He came up with this relating the charges and the distance between objects, including the insulating material and what force is created as a result of this. With electrostatic force, you're going to have repulsions and attractions. We're going to compare this to gravity in a little bit. So if you have two of the same signs, just like you see here, you would draw the force with arrows outwards. Whereas if you have opposite signs, you're going to have the force drawn inwards, and the values would be equal. Once again, from the beginning of today's lesson, we talked about the force being equal and opposite. So it's always a double force, one force on each object, but paired forces in nature. So how is electrostatic force and charge directly proportional? If charge goes up, force goes up. If this is 1 and then goes to 2, force goes from 1 to 2. And so that's because it's a 1-to-1 ratio. It's going to be called directly proportional here. Whereas electrostatic force, and so you might see FEL. Once again, it's the same thing. When you see its charges and distances, it's going to be, it is FEL. It's just not, I wasn't that specific to name it. Right here, I put a subscript. But if you were going to have subscript, it would be EL. If we have this distance, if we take a 1 and we double the distance, well, what happens, we go from 1 to 1/4. We don't go to 1/2 because of this extra square. And so that's why we call it inverse square, proportional to the inverse square of distance. Now, sometimes you're going to have equations where you have two charges that happen to be the same. So we could just call them Q and Q. We don't get rid of the second charge, but what we end up doing is just squaring it. So this is the same equation, but this is just specialized. So this is just specialized for when the charge is going to be the same. And only time really, you'll see, I'll rearrange this with you in a second. The only time this is going to be very useful is when you're trying to solve for, the question says, you have two like charges, what are they? And they give you all the other information. You're going to have to start with this one. This is the only one you can go to, and you'd have to rearrange it. Any other type of problem, if they say you have two charges that are 5 coulombs, you would just take 5 and multiply by 5. It would just fit itself into this equation. You don't have to use that one. I mean, you can. It makes it easier if you just, because 5 times 5 is the same as 5 squared. So rearranging Coulombs law, if we're rearranging it for distance, we have to get distance up top. So we distance square it on top, and then we have to get rid of force. You divide out force. That gets rid of that. Then we have to take the square root of our answer. That gets you to this first rearranged equation. You're going to be solving for all 3 of these and different, or 2 of these really, because Q1 and Q2, you do the same math to get to either one. And really, you decide what you want to call first and second charge. So there's really no need to, you can always call that charge you're looking for Q1. So if you're trying to solve for Q1, we want to get everything else. This is on top, so we just have to get rid of everything else. Whereas in the last part, D squared was on the bottom, so we had to take it to the other side to get rid of it from this side to get it to the top of the other side. We don't have to do that here. We're going to multiply out the D squared. We're going to take the k and q squared, or q, not q squared, that's q2, that's the subscript. We're going to take that, and we're going to go ahead and divide both sides by it. We're left off with q1 equals, but pay attention to these parentheses here. It's very important for typing in numbers that you keep these extra parentheses, have everything down the bottom, all this down the bottom. And even depending on how you type numbers in, it might be useful in these other equations. Especially if you have a scientific notation and you don't have a good calculator that keeps everything together, it might be useful to have extra parentheses. But these ones definitely are necessary. You need these extra parentheses down here so that the calculator can follow order of operations and keep everything down the bottom in the denominator where you want it. You want the k and the q squared to be underneath. And then q squared, it's just the same thing. Let's go ahead and move on to the next part. So this is the only time when you have two charges that are exactly the same and they're asking you for what that charge is. Well, you're going to go ahead and you're going to multiply both sides by d squared. That's going to get rid of that. You're going to divide both sides by k. That's going to get rid of that. And then you can take the square root of that answer. And that is going to be this equation right here. So you have square root of fd squared over k. Once again, it's always useful to have maybe an extra parentheses down the bottom just in case. How are charge and electrical force proportional? So as we go through this section, if you're watching the video and not at a live lesson, you should be pausing the video, answering the questions, and then watching the video. Because I'm going to go pretty quick just to go through this. You have the pause button power, so use that. It's directly proportional. This goes up, Q goes up, F goes up. How's force proportional to distance? Well, it doesn't just go down, but it goes down, it's inversely, which it goes down, but it's inversely squared right there. That's where this comes from. Okay, so when you're comparing Coulomb's law to the force of gravity. There's a couple of things you have to recognize. First of all, they're both field forces. You don't actually have to have contact for gravity or Coulomb's law, the electrostatic force. Both also have an inverse square relationship. If you take a look, this d is squared over here, and they're both related. They're both relating things to a constant, but one is going to have a. When we look at differences, let's go ahead and just move through the differences because I'll talk about what I was about to talk about. Differences. Okay, the force of gravity is always masses will always be attracted to each other. M1 and M2. There's no repulsions for masses, whereas charges, Q1 and Q2, they can have attractions, they can have repulsions. If they're opposite signs, they're going to have repulsions. So you have attractions and repulsions, either attractive or repulsive. So that's a difference. Gravity's constant. If you take a look at this number, it's very small. This is 0.0000. There's 11. You have to move this 11 times over to the left because it's negative. It's a very small number, whereas the K is a very big number. You can take this and move this because it's a positive 9 times to the right. So that's a big deal. And then just this deals with the electrostatic force deals with charges, whereas the force of gravity deals with masses. Okay, so here's a question, and what it asks you to do is, what's the strength and limitation of a model? Anytime you have questions like this, there's often a right answer and then a better answer and then two wrong answers. And that's kind of almost what you have here. What I want you to do is see this model, see how they don't change the distance in any of these models, so it doesn't do anything with distance, and that's one of the keys here. These models for gravitation shows the attraction, and it shows attraction, repulsion, and the electrostatic force. It does not show these arrows being different. So looking at these two side by side, it looks like maybe the gravitational force arrows, these things right here versus those. It looks like it could be the same size or same magnitude, which the electrostatic force we know is much greater than gravitational force, and maybe they might have wanted to put small arrows to show that. So when we're doing these problems, it does show the strength. The direction of the force differs. I can see the attractions and repulsions, but the weakness it does not correctly show. The key here is it does not show at all. It doesn't even. It's not that it doesn't correctly show. It doesn't show at all. The second one right here is going to be the right answer here. It does show the direction of forces, like I said before. It does not show that these being much smaller. So this is correct as well. And then when you get to the next parts, it is just telling you the strength is the distance. That's not the case. The distance is the same all the way throughout. This distance between the objects is the same. Okay, how much difference is electrostatic force of the charge of one object is doubled and all else remains the same? So if we have that, we set up a ratio, the equivalent right here, we put it over itself. It's equivalent to force, it's equal force, that's what that means. And then we plug in once for everything before, and plug in just changes. So here it says the object, the charge on one object is doubled. When we do that, we get an answer of 2 times. And if we knew the force was 100 newtons, let's say it started at 100 newtons and then they tell you this, well, it would be 200 newtons. That's just what 2 times means. Or you might see it increases by a factor of 2. That's 2 times as well. How much difference is force if the distance between charged objects is quadruple and all else remains the same? So we quadruple the distance, keep the distance originally the same, and we'll get 0.0625 times, or 1/16. How much difference if the charge on each object is doubled and the distance between them is quadrupled? So we take 2, both objects, quadruple the distance, we get 0.25 times. Then doing the math for Coulombs Law, you only use positives. This is going to be important here because in more detailed problems, we're going to keep the signs for the direction of the force and not the charge of the force. So we're going to only use positives for Q, and this is what I mean. So here, all objects are positive. So of course, these two numbers, the Q1 and Q2, and for the sake here, we're looking at this Q2 is a positive. But if we have this negative in front, we're going to go ahead and we're still going to use positive for the math. But when we want to answer whether there's an attraction or repulsion, we're going to go back and we're going to look at the charges. So we're going to look at these two plus and plus. Well, that's going to be a repulsion. And then if I look at this positive and this negative, Well, that's going to be a attraction because they're opposite from each other. So we'll use that. We'll use the signs. We'll go back and look at the signs to determine attractions or repulsions. We're not going to go ahead and some classes, if you have a negative force, it's an attraction. If you have a positive force, it's a repulsion. We're not going to worry about that. We're going to keep the negative and positives for directions. So here is a problem. You plug in your, it's not law once, so you're going to use the K right here. If you're typing this into the calculator, it'd be open parentheses 9.0 E9. The exponent button will deal with that for you. If you've been in my class before, you use E9, no caret or anything else, so you'll get the wrong answer. Just 9 E9 close parentheses, open parentheses, 2.1, close parentheses, open parentheses, 8.2, close parentheses, divide, open parentheses, 5, close parentheses, 2, close parentheses, equals, and you'll get this number right here. And then we turn it into scientific notation. Actually, scientific notation really would have only two numbers since these have two significant figures. It'd be 6.2 times 10 to the 9th. I just left that extra 0 on there just to kind of, so you see that that one rounded the 9 up to 0. But this is the correct answer, something around this. And it would be a repulsion because, back to looking at the signs, plus and plus would repel. And therefore, since it's repulsion, it's asking you what's happening to charge A. This B, this positive is going to cause A to want to go to the left. And so the real answer is left, not just repulsion, because of the way the question was asked. Okay, this next one, once again, you should be looking at and doing these yourself, getting the answer and then checking your answer. This next one, you would have had 850.91 newtons when you did that. And here we have microcoulombs. So this is where you have to watch out. You're going to have that times 10 to the negative 6, or in the calculator, it would be 13e negative 6 if you're doing the exponent button. And it would be attraction because it's positive and negative. This next one would be 3.75, and it's positive, it's negative and negative, so it's going to be a repulsion. Once again, make sure you're doing it yourself and pausing this video just to check. This one you have to use the rearranged equation, and if I was typing this into the calculator, I'd have the square root of open parentheses 9e9, close, open, 4.5e negative 6, close, open, 8.8e negative 6, close, hit the divide, 6.4, close, equals, and you should see this number, 0.236 meters. This next question is asking you for charge. So you have the rearranged equation. You plug in the values, open parentheses 40.2, close, open, 5 squared, close, divided by, open, 9e9, close, open, 0.1, close, equals, and you should see this value right here, and the unit is always going to be coulombs for charge. You don't have to worry about turning this back into a prefix. This would have been 1.12 microcoulombs. That's fine. You can keep it as this. An attraction force of 1.1 is exerted between two objects 45.43 meters apart. One charge is this. What's the other one? So when you do the math here, you should get 3.96 times 10 to the negative 6 coulombs. And then lastly, this is a more detailed problem because we're looking at B is going to interact with A, B is also going to interact with C. We're not interested in what B is doing to A. We're just interested in what A is doing to B. So we're going to take this and we're going to do this in two parts. We're going to kind of ignore this C and we're just going to deal with A and B. And we're going to take the charge for A. We're going to take the charge for B. And once again, if you have any positives, you're going to make negatives. You'd always make them positives. But here we only have positives, so it doesn't matter. And you'd find that there's a force of 1.06 times 10 to the 10th newtons. And what's happening is to B, because once again, we're only concerned with what's happening to B, this positive and this positive, because you have a positive here, it's going to push B to the right. And so this would be part of our final answer. We're not there yet. This is one step. We found the A. So once we're not concerned with A anymore, B is going to be pushed to the right by this force right here. Now, for the second part, we want to go ahead and we want to figure out, now let me just talk to you about my subscripts. This just means A to B. This just means B to C. So now we're concentrating with B and C. Well, B, this 9.5 and this 4.1, when we find the force between these two, which are also 5 meters apart just by chance, we're going to get a force of 1.4 times 10 to the 10th. But we have to say, okay, we're only concerned with what this positive charge is doing to this positive charge. And that's going to be pushing, that is going to repel B to the left. So we're only concerned with what's happening to B because of the question. If the question was different, we might be concerned with A or we might be concerned with C, but the question's not asking that. So what's the force on B? Well, now we're going to go ahead and we're going to take this direction. We're going to call this negative for left. We're going to call this positive for right. We're going to go put those together. We're going to add the vectors. We're going to get an answer, and then we're going to look at that sign of our answer, and that's going to give you an overall. Since it was negative, we're going to go ahead and call that left. So this would be 3.4 times 10 to the ninth newtons left as your answer.